All right, let's take a look at a really nice result we get when we combine our line integrals in a vector field and conservative vector fields. Now remember, for a vector field to be conservative, so if we have some vector field f, if it is conservative, that means that it's the gradient of some other function. Let's not confuse this, let's just call this some function g. All right, now I'm going to run you through this why what happens here kind of works. Now what I'm going to show you is wrong, but it kind of gives you an idea of what we're talking about. Remember, these are the integrals we're looking at right now. We're looking at f dot dr. Again, this is wrong, so just to get you kind of the idea of why this works. Well, if f is the gradient of some field, that's del g dot dr. Remember the gradient here, you can kind of think about that. That's the partial of g with respect to x, partial of g with respect to y, dotted with dr. If you think about that in your differential form, that would be dx or dy, right? Because it's the differential, the derivative in the x direction, derivative in the y direction. Now, if you notice, if you dot these together, when you multiply the x stuff together, you just get the derivative of g, or the partial of g, and with the y. So you can see, again, this is where this is wrong, that what you end up with is the integral of the derivative of g. Well, we know the integral of the derivative just gives us this value g. Now, if we had endpoints on here, let's say we had a to b, all we'd have to do is evaluate this from the endpoints. So the idea here is if we are doing this work integral in some field, and the field is conservative, all we need to do is find the potential function for that field and evaluate it at the endpoint minus the starting point. All right, let's take a look at an example of this real quick, and we're going to see why this can be so important. So let's say that I tell you to do the integral of f dot dr. I give you f here is, let's do 2x cosine y, negative x squared sine y plus 2y. And let's say the curve that I gave you is this. We want to make it out here to the point, I don't know, 4, 4. And I want to go along this line first. Then I want to say we want to go up here to 2. Then I want to go along the parabola that gets me from there to there. So in this case, this would be C1, C2, and C3. So this curve is made up of 3 pieces. Now, to do it the way that this says, we'd have to parameterize each one of these curves and then do what? Plug the x, y values into here, dot them with the dr for each one of those curves, and then add up all the results. That's a ton of work. What you always want to check when you're doing the integral of f dot dr is if f is conservative. Now remember, the test for conservative is if m sub y is equal to n sub x. Now here's our function m. If we take the derivative of this with respect to y, I get negative 2x sine y. If I take the derivative of this, this is n with respect to x, I get negative 2x sine y. Which means f is conservative, which according to what we've shown, we don't actually need any of these curves at all. All we need to do is find the potential function and evaluate it at the first point and the last point. So to find the potential function, remember what we're going to do. We're going to integrate the x component, cosine y with respect to x, and we're going to integrate the y component with respect to y. Now both of those should give us our answer within an integration constant. So if I integrate this with respect to x, I'm going to get x squared cosine y plus any function of y. Over here, if I integrate this with respect to y, I'm going to get, did I got something wrong? Oh, this is x squared. If I integrate this with respect to y, I'm going to get x squared cosine y plus y squared plus any I don't know, function of x. Now remember, both of these need to be our answers. So the way to either figure out what h of x and or our h of y and f of x is, we set these two equal to each other and see if we can figure out what the missing pieces are. Cosine y plus y squared plus f of x. Now again, at this stage, if you're doing this, and functions that have both x's and y's in it aren't on both sides, you've made a mistake somewhere. So notice here we end up with h of y is equal to y squared plus some f of x. So whatever the function of y is on this side has to be the function of y on that side, so h of y has to be y squared. Whatever the function of x is on this side has to be the function of x on this side, so it's obvious f of x has to be 0. So notice if we put h of y equals y squared into here, our f of x equals 0 into there, we get the exact same function. So our potential function, and again I'm going to start up here at the top, would be potential. Let's give it some room. Our potential function is, what did I call it? Let's call it g of x and y. X squared cosine y plus y squared plus any other integration constant. Now, since we're going to evaluate these at endpoints, like any definite integral, we don't need that integration constant here, but it's going to work. So all we have to do, if we want to find the value of this, is we're going from the point 0, 0 to the point 4, 4. So the value of this, the integral of f dot dr, where that's defined to be our path, is going to be x squared cosine y plus y squared evaluated from 0, 0 to 4, 4. All right, put in the top endpoint, that's going to be 4 squared cosine of 4 plus 4 squared minus 0 squared cosine of 0 plus 0 squared, or our answer is going to be 16 cosine of 4 plus 16. Okay, whatever number that is, that will be our value. Now notice how much easier that was than trying to parameterize each one of these curves and doing f dot dr on every single curve. Now, also what that means, one of the most important results from this, is you're doing this integral of f dot dr, and f is conservative. Hold on, draw my picture back. And if f is conservative, it's called path independent, which means you'll get the same answer no matter what direction you take here, not through some weird zigzaggy thing, but you could go directly there, you would get the exact same answer that we got there. You could start at the origin and wiggle your way up there, some weird sine curve thing, you would get the same answer. So it's called path independent. So the integral of f dot dr, if f is conservative, is path independent, which means you can take any path there that you want. So if you're given some curve C and you know it's conservative, well, you could do the potential function, or you could find any parameterization you want to go from point A to point B, from your start to your finish. Now there's one more truly wonderful result about this that can save you lots and lots of work. We solved in the last lecture, if we're doing an integral in a field, some f here, where we're existing in some world f, if we went one way in the field, we went that way, we got one answer, and if we went the other way, we got the same answer but the opposite sign. Well, if we combine that with our conservative vector field, what does that mean? Since it's path independent, and I'm just going to kind of draw a picture, since it's path independent, whatever path I take to here, I'm going to get the same answer. And if I start here, whatever path I take back, I'm going to get the opposite answer. Now notice what we ended up here with. We ended up with a closed circle or a closed curve. So anytime you do an f dot dr and inside of a conservative vector field, if that curve is a closed curve, what does the answer have to necessarily be? Well, whatever the value is for this side is the opposite of it. Once you go to 1, you get one answer, it doesn't matter how you get there. And then when you go back the other way, you get the opposite answer. So the work done here would be the work in one direction plus the work in the other direction, which would be 0. So anytime you're integrating in a conservative vector field and you have a closed curve, the answer is always 0. Right, so let me put that result up here. If f is conservative, f is path independent, and the integral around c of f dot dr is equal to 0 if c is a closed curve. So you start to see the reason why this might be important, especially if you notice that c is a closed curve. You always want to check to see if f is conservative. Because if c is closed and f is conservative, you don't have to do any work at all. You know that that answer is 0. So keep an eye out for that in the homework and really save you a lot of work.